I've mentioned several times when discussing entropy how the universe likes entropy, right? And this actually has to do with the second law of thermodynamics. So the second law of thermodynamics states that the total entropy change of the universe must be positive for the process to be spontaneous. So overall, for something to be spontaneous, the universe wants there to be more entropy gained overall. So for a reversible process, we have an entropy change of 0 because you're going to one side of the reaction and then coming back. So overall, nothing's really changing because it's in equilibrium. So overall, you have the rates of both of them, forward and reverse reactions, being the same. For irreversible or spontaneous reactions that only happen one way, like from reactants to products, the change in entropy of the universe will be greater than 0. So the universe wants this to happen and it wants it to stay there where whatever you produce for the products. If the entropy of the system decreases, then the entropy of the surroundings have to increase by a large amount. So if, for example, you start off with 2 moles on your reactants and you end up with 1 mole on your products, this is overall decreasing entropy for our system, right? If we're just looking at this chemical reaction as our system, then what has to compensate this is the entropy of the surroundings increasing by a large amount. So the overall entropy change of the universe is equal to the change of the system and the surroundings. So when the change of the system is negative, meaning you ended up having less entropy, the change in the surroundings must be positive in order for this to happen on its own as a spontaneous process. So in terms of heat, we can look at heat as flowing. So when ice is placed in water, heat will flow from the water into the ice. According to the second law, heat must flow from the water to the ice because overall it ends up causing more dispersal of heat. So if this water is, a little bit hot or just warm, and you have this ice in there, it's going to melt the ice. The molecules that were originally very ordered and, rigid in the ice, they will dissolve and now they're free to flow, which causes higher heat overall because if the molecules are flowing, they have more kinetic energy. More kinetic energy translates to more thermal energy, which is a higher temperature. And overall, this will cause more entropy in the universe. In the previous example, we were going from a solid ice cube to a liquid. So that is an increase in entropy, right? And we were also causing an overall increase in heat flow. So that again contributes to that increase in entropy. But what about for an example where we are going from water vapor, so a gas, to a liquid when it's condensing? In that case, it's still spontaneous. I mean, you see it happen every day. If you have a cold water bottle in your fridge and then you pull it out to sit on the table, you're going to start to see condensation form on the outside of the water bottle. And it happens on its own, completely by itself. So it's spontaneous. But this gas to liquid is a decrease in entropy. So how is it happening? And this has to do with the fact that there is a large increase in entropy of the surroundings. So the process itself is unfavorable, right? We're decreasing in entropy. But overall, it happens because of the change in entropy of the surroundings. So the entropy increase must come from the heat released by the system, and the process must be exothermic, which is true. Whenever water condenses, you're losing heat from it being a gas, and in order for it to come together and be a liquid, that heat has to be lost. So it is an exothermic process. So even though we have this decrease in entropy, it being exothermic makes up for that and allows it to be spontaneous. So this is a visual representation of what we just talked about. So whenever we have water condensing, I might as well just write it. We have a decrease in entropy of the system, right? This is increasing this way, so this would be decreasing. But the surroundings entropy is increasing because of the heat flowing out from water condensing. So overall, when you sum these up, this one and this one, we get the change of the universe, which is slight, we get some entropy from it. So this overall makes it spontaneous. So the temperature of the like the starting temperature, for example, of water before it freezes, affects the overall net change in entropy. So let's say, for example, you have a low temperature of water. Whatever change occurs whenever it's giving off enough heat so that it freezes will cause a greater change in entropy to the surroundings. So when something is already at a low temperature, for example, water, and it reaches that low enough temperature so that it ends up freezing, that heat given off in order for it to freeze finally is greater than if it was starting off at a very high temperature. So you'll have a bigger change in entropy for the surroundings, meaning you'll have more heat given off and it'll have a greater impact on the surroundings, versus whenever you're starting off with a high temperature, it won't be as much heat given off. And then this causes a difference in net. So here we have a negative net change in entropy. Here we have a positive. So here we'll have a spontaneous change, and here we'll have a non-spontaneous process. So we can actually relate heat and temperature to entropy. So heat is directly proportional to our entropy. So if you have an increase in heat, then you will have an increase in your entropy, S. On the other hand, temperature is inversely proportional. So if you have an increase in temperature, then you'll have a decrease in entropy. And because of that, we can write out this mathematical relationship. So if you increase heat, then your delta S, your entropy change, will increase. But if you increase temperature, since you're dividing, this is like the inverse. If you increase your temperature, then this will decrease. So we're going to be using this relationship in the following example. So in this example, we will be looking at whether a process is spontaneous or not, so whether it'll happen on its own. So we have this process occurring. We have ice essentially turning into liquid water, and it has an entropy change associated with it. It requires that these surroundings transfer 6 kilojoules of heat to the system. So the surroundings is giving this heat to the system. So that wording is important because that is going to tell us the sign of the Q. And it's actually negative because it's giving that heat away to the system. Is this process spontaneous at negative 10 degrees C, and is it spontaneous at 10 degrees C? So I'm actually going to do the second portion. So this first portion, I did that problem in the problem solving session, and I'll do this one just so that you have both. So here we are going to lay out what we have so far. We have the delta S of the system. That's just the entropy associated with this ice turning into liquid water. That's a 1. That's a J. And we also have our Q of our surroundings equal to 6.00 kilojoules, and also we have our T, or temperature, at 10 degrees C. Notice that our units for our entropy is in joules over Kelvin. So we want our other values to also match. So we're going to have to convert this kilojoules, 1 kilojoule, to 1,000 joules. So we multiply it by 1,000 basically, and you will get joules. Kilojoules cancels out. And to convert this to Kelvin, we would add 273.15 Kelvin. So that gives us 283.15 Kelvin. Now we have everything ready to plug into our equation. So this part right here is the delta S of our surrounding. So it just replaced that, and it's the relationship we just talked about on the previous slide. So to get our overall delta S of our universe, we will have our 22.1 joules over Kelvin for our delta S of the system, plus the 6 times 10 to the third joules divided by, that should be 6.00, sorry, divided by 283.15 Kelvin. And overall you should get positive 0.9 joules over Kelvin. So what does this positive tell us? This positive tells us that our entropy is increasing, right? A positive entropy is good. Entropy is increasing, and overall this means it will be spontaneous. And this makes sense, so think about what's happening. We have ice turning into water, and we know that the freezing point of water is 0 degrees C. Anything below that will cause the ice to stay frozen unless, you put some heat into it, or anything above it will melt. So, room temperature is what, 25 degrees C, so this isn't too far off there from that. It's pretty hot compared to the ice, right? So because of that, we should see it melt on its own. Like if you have an ice cube on your hand in room temp, for example, it will melt. So this makes sense that it is spontaneous. So there are some conditions that scientists have coined standard conditions. These standard conditions are just set conditions. So for gases, they are exactly 1 atm of pressure, solid or liquid, in its most stable form at exactly 1 atm pressure. And the temperature is usually 25 degrees C, which is also 298, I was going to write a degree, 298 Kelvin for a solution, so like a liquid. The substance will have a concentration of 1 molar. So now we have reached the third law of thermodynamics, and this law has to do with something called absolute entropy. Absolute entropy, this definition is going to sound kind of vague, but don't worry, we're going to break it down. It is the amount of energy a substance has due to its dispersion of energy through its particles. So the third law states that for a perfect crystal at absolute zero is 0 Kelvin, and at absolute zero, the absolute entropy is 0 joules per mole Kelvin, or joules per Kelvin. That's the unit for entropy. So because of that, we can say that every substance that is not at absolute zero, and it's not a perfect crystal, what we term as a perfect crystal, meaning it has only one W value and it has an entropy of 0, will have some energy. So anything not falling in these very specific sets, like set of conditions or set of characteristics, will have some sort of energy from entropy. And basically that's a lot of things, right? So the absolute entropy of substances that we measure is always positive. So standard absolute entropies are absolute entropies that we have measured, and specifically we've measured them at standard state. So remember I had a slide on standard state. It was kind of random, but it was because we need to tie it to this. So these entropies have been measured for 1 mole of substance at 298 K. Remember 25, that it's typically at 25 degrees C. For a particular state, a particular allotrope, or, you know, it's very specific depending on whatever you're looking at. But we have a specific absolute entropy for it, and we denote it with S with the little knot. This is an extensive value, meaning it depends on the amount. So if you have more, the number will increase. If you have less, the number will decrease. It's not based on the type of substance. It does depend on how much, and you know the rest of these characteristics. So here are some of those standard absolute entropies for these substances that are listed. So for a bunch of gases, a bunch of liquids and solids, so you can see that all of these have a positive entropy, and depending on whatever properties each substance has, the entropy changes. So these are just very specific values, and just know that we do have these measurements already there, so you can go to this table if you ever need it. If you're doing a homework problem or something, just look at the tables in the book that have them. Now we're going to go through how each type of characteristic, how it can affect the standard entropies. So for example, states. The gas state will have a larger entropy than the liquid state at a specific temperature. The liquid state will have a larger entropy than the solid state. That's something we've already gone over this concept, with just talking about basic entropy. Now we're talking about a very specific entropy that has been measured, the standard absolute entropy, but it still applies for this case. And here we see the example of water. So we have liquid water versus gaseous water. The entropy is obviously higher for gaseous water because the molecules are free to move around. They have more degrees of freedom. They're more random, so you have a higher entropy. Next is molar mass, and main idea of this is that the larger the molar mass, the larger the entropy. So we can see here as these atoms are getting bigger, these are all the noble gases. As we go bigger, for example, this xenon, the xenon has an entropy of 169 versus up here this tiny little helium is 126, and you can see the pattern right there. So this has to do with the fact that the energy states that are available are more closely spaced, which allows for more dispersal of energy throughout the states. So the fact that there's this atom is bigger allows for this to happen, and overall contributes to a larger entropy. Next we have allotropes. Allotropes, what they are it's the same element and the same state, except they're somehow bonded differently. They have some sort of different bonding network. And the easiest example, which I have mentioned before, is diamond, so carbon solid diamond versus carbon solid graphite. These are both carbon solids, except, obviously you know what diamond looks like versus graphite. And the way that allotropes, so these are allotropes to each other, the way that allotropes affect entropy is that the less constrained the structure of the allotrope, the larger its entropy. So you see how graphite is in layers and it's not bonded together, versus right here, it's in layers, right? You have one sheet right here, one sheet right here, one sheet right here. Versus carbon, there's this really ordered network structure going on here. Every carbon atom connects to another one, and it's just, think of it kind of like a honeycomb, but in 3D, in three dimensions. Versus this is just in these flat layers. this is a lot more constricted. This is less constrained, less constricted, so there's more entropy here in this allotrope. We also have a factor called molecular complexity. Molecular complexity has to do with molecules. So if we compare a molecule to, so this is a molecule, to a singular, monatomic atom, or a monoatom, you can see here how this is larger based off the molar mass, right? And this is a little bit smaller. But here, this entropy is 154 versus 210. So the fact that this is a molecule and not just a singular atom contributes to its molecular complexity. So it ends up having a larger entropy. And we can also see this here with this smaller molecule versus an even bigger molecule. So here we're comparing an atom versus a molecule, right? Sorry, my handwriting's horrible today. And then here we're comparing two molecules, but one is bigger. So this one, well, actually, they're about the same size, 28 to 28. But you can see how the fact that there's more atoms in this compound overall, this molecule, it has a higher entropy. So generally, the more complex molecules, larger and more complex molecules will have a larger entropy. And again, this has to do with energy states that allows for more energy to be dispersed. So in terms of this energy that I've been talking about, what does that mean for molecules? How does it look at the molecular level? Molecules are constantly moving around, not only, especially if they're gases, but even if they're like solids and liquids, if they're moving a lot slower than gases, but they do have a lot of motion associated with them at a very small level that you can't see, obviously, with our naked eye. But we have translational motion, rotational motion, vibrational motion. There's a lot of motions that are going on at this very, very small atomic / molecular level. And this is what we're talking about in terms of energy for these molecules. Finally, we have how dissolution affects standard entropies. So dissolved solids generally have a larger entropy because they can distribute throughout the mixture. So here we have solid potassium chlorite, I believe, versus aqueous potassium chlorite. Obviously the aqueous, it has dissociated into solution, so it has a higher entropy associated with it. So if you remember, but if you don't, it's okay. But if you remember from Chem 1, we learned how to calculate something called standard enthalpy of formation. And basically what we did here was we had standard values, like remember on that table with the entropies that we just looked at? We had values like that, but for enthalpy. And we could calculate the overall change from like adding up all the enthalpies for the products and then subtracting the reactants. And we can actually do the same thing here with our entropy changes. So the standard entropy change is a difference in absolute entropy between the reactants and products under these standard conditions. With enthalpy, we have something kind of special where the enthalpy change of an element, meaning either a metal like solid or one of the diatomic elements, for example, H2 gas, anything like that will have an enthalpy of 0. But for absolute entropy at 25 degrees, remember anything above 0 Kelvin, you will always have an entropy associated with it. Here we'll always have an entropy, even if it's just like the standard state element. So now we're going to determine a change in absolute entropy. And here what we have is the combustion of methanol. This is methanol reacting with oxygen, methanol and oxygen, and they are reacting to form our combustion products, which are always CO2 and H2O. So what's important here is knowing where to get the standard entropy changes, which comes from this table or whatever table you're using. You can find these in whichever textbook. But I am using the ones from our textbook, so I just want to have, another table here just so that you know where I'm getting it from. So it's any table that has our standard molar entropies. So I listed them all out because I know it's hard to see, it's kind of small. So I listed them out, and now we are going to use them. So we are going to first add up our products. So anytime you see this weird like capital E, that's sigma, which means sum. So we are going to add up all the entropies of our products first, and then subtract away all the entropies of our reactants. So for our products, so you can do it step by step, it's up to you, or you can do it like in one giant step. I like to do it step by step so I can see what's going on. So our products, we have CO2, specifically we have 2 mole of CO2. We're going to multiply it by the entropy associated with it. And you're going to do this for everything. Joules, 0.8 joule per mole K. That cancels out the mole. And then what you're going to add to it is the water. So 4 mole of water times our 70 joule mole K. So the mole cancel out. So then we can calculate that out. I'm going to just leave it like that and do it on my calculator. And from this we are going to subtract. So just make sure you have that correct sign. And for the reactants, we are going to subtract away the methanol. So it's 2 mole of methanol. 2 mole times 126.8 joules over mole K. Mole cancels out. Plus the oxygen, which is 3 mole. Times 205.2 joules mole. Okay. You do that step, subtract it away from the first number you get. Overall, what we should get is negative 161.1 joules over K. So that is our standard entropy change. And that's a negative, so obviously, this is decreasing in entropy. And you can see it here. So we start off with 3 moles of gas, and we end up with 2 moles of gas. So overall, this is decreasing entropy.